and welcome to Math 125 Calculus 1. This video is going to cover Introduction to Calculus and some pre-calculus review. Calculus is the study of change. That is a study of change when the elapsed time is extremely small, that we call it infinitesimal. And then what we are trying to get into this course is to be able to calculate the behavior of mathematical models. And so we will introduce you to some mathematical models. We give you word problems to work out the calculus of the models, and then you will see that even though these are simple models, a more complicated model can basically break down into the simple models that we introduced. A lot of them, not obviously all of them. Some of them you have to start with completely different models of mathematics. So the first chapter that we cover in this course is chapter 2. It's limits and continuity. In how does limit and continuity work with these course is first of all explaining this infinitesimal comes with limits, and infinitesimal changes are what we discuss with limits, and then it also helps with finding the behavior of models in some places. Concept of limits and continuity comes back in follow-up chapters, chapter 3, 4, and 5. Every time we discuss a new concept, we have to go back to the limits and continuity. So one function that is familiar to you is y equal to x squared minus 1 over x minus 1. This one or this type of function is familiar to you. This is the type of function that you see when you discuss continuity or domain of an elementary function. This function everywhere in its domain works as y equal to x plus 1. Except that is not defined at x equal to 1. Basically, continuity for elementary functions is that the function is continuous with the elementary functions are continuous in their domains. But then easily enough, there can be a hole in the function, and that hole causes a discontinuity. In this case, basically a lot of limits exist, but the function has a hole, so discontinuity happens. The next concept that comes basically on its own, we discuss limits again as the behavior of a function on asymptotes is defined. Closest asymptote is defined as a limit. Basically, all the concepts that we learn about asymptotes becomes a limit, and that again tells us more about behavior of a function as the end behavior of the function, or if there's a vertical asymptote, how does a function behave, getting closer and closer to that asymptote, basically. All of that said, there are other types of functions that we discuss for limits and continuity. One of them can be this type of function. If you see that y equal to x sine of 1 over x, domain does not include 0. So if I want to define this over the entire real numbers, we have to make it into a piecewise defined function. And it's interesting because there's so much oscillation happening right there, but then you kind of see the trend of function going toward sort of this point that is not there as it did over here. So what else we cover? Chapter 3. That's the rate of change. What we remember from PreCalculus is the slope of the secant line is the average rate of change of the function at these 2 points. So if you have 2 points, the slope of their secant line gives you the average rate of change. So here's a secant line. Now I want to know whatever is the rate of change at a point A and F of A. So the rate of change at area of A and F of A, it's supposed to be something that comes basically as a behavior of the secant line around A and F of A. And so what happens is that if you look at all these secant line, at some point when B gets closer and closer to A, the secant line becomes a tangent line. That means that it locally touches the function, the graph of the function only in 1 point. And that basically it again defined by the concept of the limit, it gives us instantaneous rate of change. And that's the discussion of chapter 3 and some more over that. And then we drive a lot of formulas for this instantaneous rate of change. The next chapter, chapter 4, it talks about the shape of graphs of the function. And now that we know a lot about shape of graph of a function and how it explains the models in PreCalculus. But now calculus gives us a lot more tools to discuss the function using the graphs of the function. So it gives you enough information for the graphs of function. And so something that is covered in chapter 4 is these local maximum, local minimum, and so on and so forth. And we also discuss what is called absolute or global min and max of a function. So this is very useful for optimization. So you have a situation and you model it with mathematics, and then you sometimes want to have the optimized situation. You either want to spend less money, or you want to get more out of whatever money you have, and so you want to optimize the outcome of the events. And so this chapter we model a few of those. The next is chapter 5, and then chapter 5 discusses the area under the curve. And so area under the curve, because what the area that we're very familiar with is the area of a rectangle, or their shapes that we are very familiar with on how to find the area of them. And we use this concept of infinitesimal change again, and we basically tile under the curve using rectangular shape to find the area under the curve. And that, again, in chapter 5, ends up with the fundamental theorem of calculus. So what we learned in chapter 3 was a concept called derivative. Now in chapter 5, we learn something called integral. And then this accumulative function that we learn in there is related to this integral. So fundamental theorem of calculus gives you a function basically that is anti what we did in chapter 3. And so that is another part that is of interest to us, basically. So these are all the basically some of the concepts that are interesting in each chapter, and or explains what each chapter is going to be about. Now let's talk about pre-calculus. What we remember from pre-calculus, there was a function is a black box. There's an input going in and an output going out. Usually x comes in and y goes out. So it's y equal to f of x, basically. There's a vertical line test for functions. For example, this first one, the oval over here, is not a graph of a function. But over here, this parabola is a graph of a function, because any vertical line only intersects a parabola in one place. So there are some graphs of well-known functions. This one is the constant function. Then we have the identity, that's y equal to x. Then the graph of the function f of x equal to absolute value of x. See, it looks like the identity that is broken and one piece basically mirrored over x-axis. And then the graph of a function f of x equal to x squared, that's the parabola looking upward. And so inverse of that has to be restricted, because this is not a one-to-one function, and the inverse is absolute value of x, but the domain of the inverse is basically restricted. And then other functions, f of x equal to x to the x cubed, and that there's the inverse of that one is the third root of x. This one is not basically restricted, because you can also take the third root of negative numbers. Even roots are always over the positive numbers, for real numbers, and the odd roots can accept the negative numbers also. So it's both positive and negative for these. By the way, your calculators, usually they're mini calculators that don't have the tools to take the third root of negative numbers. You just have to remember to plug in the absolute value of the number and basically negative of the third root of the absolute value of the number for when x is negative is going to give you the answer. Then we have these type of functions that are quotient functions, f of x equal to 1 over x. If we go for f of x equal to 1 over x squared, then the shape, basically a part of it, becomes a mirror image. Equation of a line. So when we're talking about equation of the line, we're talking about point P1 x with x1 and y1 as coordinates, and P2 as x2 and y2 as coordinates. And then the slope of the function is the rise over run. That's the difference in y2 minus y1 over x2 minus x1. Oh, by the way, you can switch the two and for the slope. If you write y1 minus y2, then you have to write x1 minus x2 in the bottom, basically. And so then b is let's say the equation of the line, the slope intercept of this is going to be y equal to mx plus b, where b is the basically y intercept of the line. And this is called slope intercept form. There are other forms, but then basically you can always simplify to slope intercept form. And the other thing to notice is that graph of a linear function is a line. Now let's talk about trig in exponential and logarithmic graphs. We start with the cosine and sine. The cosine function is illustrated in one period. That means that it just goes on and on like the same wave. Basically, it repeats this entire thing. If you notice, cosine is 1, cosine of x is a 1 at x equal to 0, and then it's 0 at pi over half, and then it becomes -1 at pi. And over here also things to notice. Y equal to sine of x is again another wave, and it repeats it. This is again illustrated for period 2 pi, basically for a period of the and starting from -pi to pi, and then it repeats its cycle as it goes either side, as did cosine of x. So basically the same shit goes on and on. Then let's talk about tangent of x. Tangent of x is one of those functions, again, very much of our interest because it's again comes back in chapter 2 a lot. We have to remember how these basically graphs look like. The vertical asymptotes and horizontal asymptotes are important to us. When cosine and sine did not have any asymptotes at all, they would just they were periodic and they would repeat themselves over and over and over again. Tangent of x is periodic, but with an asymptote, a vertical, with infinitely many vertical asymptotes. So for example, at pi half, where does the asymptote appear? When the denominator is going to be 0. So if I tangent of x is equal to sine of x over cosine of x, and that's the simplified form, and cosine of x equal to 0 gives you pi half, it gives you -pi half, and so on and so forth. By the way, the period of tangent of the x is going to be just pi, is pi because it just repeats after every pi. Now, the inverse of tangent of x is arctangent of x. Arctangent of x is one of those inverses that actually is restricted domain. See, it's just the inverse of the main branch of the tangent of x, and the other ones are not included because tangent of x is not one-to-one. We have to choose a main branch, and that's the main branch that we choose. Now, compare these two. Tangent of x has vertical asymptotes, and arctangent of x has horizontal asymptote, and that's what you expect from inverse functions. Tangent of x has infinitely many asymptotes, but because arctan of x is restricted, is inverse of the restricted tangent, only has 2 horizontal asymptotes. And then other functions, here's an exponential, y equal to e to the x. As the exponent over here goes toward the negative infinity, there is a horizontal asymptote, y equal to 0 for e to the x. And so you're expecting for the inverse to have a vertical asymptote because e to the x has the horizontal asymptote, y equal to natural log of x, and basically has a vertical asymptote at x equal to 0. Now, iClicker question 1. Values of the function f and g are given in the table to the right. The value of g of f of 3 is, and the choices are a equal to 1, b equal to 2, C equal to 3, and D equal to 4. And so give yourself a little time to work it out and come back. Okay, and the answer, how do I find G of f of 3? First, I have to find what the value of f of 3 is. And so to find the f of, because that's the inside, and so f of 3 over here, 3 for x, f of 3 equal to 4. And then calculate G of, so you have to calculate G of 4. G of 4, this is x equal to 4, and that G of 4 is equal to 1. And so that's the answer.